Metathesis reactions usually will have at least one ionic compound present. For an ionic compound to react, it needs to be in its aqueous form because solid ionic compounds are incredibly stable and unreactive. Therefore, we have to take that solid ionic compound, which we typically call a salt, an ionic salt, and we need to dissolve it into water to have it become aqueous. We will take two aqueous ionic compounds because they need to be in their ion form to allow electrons to move to form new bonds. What happens if a metathesis reaction occurs is one of the products is going to have a state of matter change. So you're going to start with two aqueous solutions as your reactants, and they're going to interact. And based off their interactions, if one of the new compounds comes out as a solid or changes to a liquid, the reaction has taken place. If they stay aqueous, no reaction actually occurs. So this is how we can tell whether or not metathesis reaction takes place. We do this based off solubility. So solubility is the ability of the salt to go into water. As you can see with this image, water will surround each of the ions of that salt to free them from their ionic compound. If a salt is insoluble, the attraction with water is not strong enough to separate the ions from each other. In order to determine whether or not a metathesis reaction occurs, we need to know whether those ionic compounds are soluble or insoluble in water. We can use a set of solubility rules. You do not need to have this table memorized. It is provided to you in your chem data sheet. You just need to know how to apply the information on here. All right, so we have two different categories, and I'm going to draw a line. Oops. My screen is getting hot. So we have our water soluble, and we're focusing on ionic compounds, versus our water insoluble. So water soluble means the attraction of the ions to water is strong enough for water to pull the ions apart and dissolve into water. In the water insoluble category, the attraction of the water to the ions is not strong enough to pull those ions apart. With reading this chart, starting from the top, it's a hierarchy. So where I've starred is more important and takes priority as we go down, ending with this other side. So group 1 alkali metals, sodium, potassium, lithium, ammonium, NH4+, they're always soluble. There are no exceptions. If you have another ion with these cations, it will go into water. That is important because if we have certain elements that do not dissolve readily, we put them with one of these compounds, it will go into water. So that starts off with our priority. Second in priority are the anions that are always soluble. So nitrate, acetate, chlorate, perchlorate. So starting at step 3 with our halogens, most halogens are soluble. However, when they interact with heavy metal ions, they will form bonds with those heavy metal ions, like lead, silver, and mercury. Because of this, we know that we can get lead, silver, and mercury out of water by adding some chlorine to it, and it's going to pull it out so that we can have safe drinking water. Then we have sulfate, is in the water soluble, but we have its exceptions. So if sulfate is interacting with a group 2 metal, so your alkaline earth metals, it will come out of solution and become a solid, or our heavy metal ions. So here we are starting with our aqueous, and if it falls into the exception category, it's going to stay a solid. On the other side, we have our water insoluble, and so this is where these are going to stay solid with the exception of becoming aqueous. So hydroxide and oxides are insoluble unless they're with the group 1 metals, your alkali metals, ammonium and barium, followed by our sulfides, and then our carbonates and phosphates. All you need to be able to do is identify one of your ions on this chart and know if it can be soluble or insoluble. So let's practice this. Here we have a reaction. It's already balanced, written, and everything for you, but does this reaction take place? We can determine if this reaction takes place by looking at the state of matter. If they all stay the same, no metathesis reaction occurred. If one of those products changes states of matter, a metathesis reaction has happened. Starting with our first compound, we've got sodium sulfide. So I'm going to look at what I have present here. I've got a sodium ion with a sulfur ion. I'm going to look at where do these fall. Sodium is in the water-soluble ionic compounds. It is a group 1 alkali metal where it is always soluble. So even if we look at the insoluble side, sulfide is always soluble with group 1 metals. Therefore, sodium sulfide is aqueous because it is soluble. Looking at our next one, magnesium. So magnesium is not in this list. It's going to be dictated based off its anion. So our anion is chlorine. So when we look at this chlorine, where does it fall within this chart? So chlorine's down in the 3rd level. Chlorine is soluble except with heavy metals. Magnesium is not in that list of heavy metals. Therefore, this chlorine will allow magnesium to be soluble. Therefore, this compound is soluble. This has to be here. These two have to be soluble in order for a metathesis reaction to occur. So you should always have aqueous reactants. It's what is happening in the products. Going to sodium and chlorine, sodium is always soluble no matter what. Chlorine is soluble unless with a heavy metal. Sodium's not a heavy metal. So that stayed aqueous. Magnesium's not on the chart, so we need to look at the sulfide. Sulfide, as we saw, is only soluble with group 1 metals. Magnesium's a group 2 metal, ammonium or barium. Magnesium is not on that exception list. Therefore, this is a solid. That means it's coming out of solution. It is a precipitate. This means that this metathesis reaction did take place because a change occurred. In redox reactions, we look at the half reactions to see the transfer of electrons to know whether or not that reaction takes place. With metathesis reactions, we need to identify the phase change and which ions are participating in the phase change. Those ions are really the reaction we are looking for. So it starts to ignore the spectator ions or the ions that were present to allow the two reactants to be aqueous in the first place. So how we do this is through a set of 3 reactions. We want to write and balance our traditional, what we call formula equation. So this is going to be your balanced reaction with the state of matter for each compound. If a phase change occurs and metathesis is happening, then you move forward. If a phase change does not occur, metathesis did not happen, it's not a metathesis reaction, so it doesn't do anything else. So let's say one worked, and we're going to move forward. What we're going to do is we're actually going to look at this in its ion form, because that's what aqueous means, is that our ions are present. So we're going to split up our aqueous solutions into their ions. If you have a solid compound that was formed or a liquid compound that was formed like water, that stays as a compound. It is no longer aqueous, so it's written as one full compound. We are going to cross out anything that stayed aqueous or an ion on both sides of the reactants and products. What remains is the net ionic equation. That is the reaction we care about. What are the 2 ions that we needed to interact to form the product we are looking for? We're going to practice this, so you'll probably want to have your chem data sheet available for solubility because I didn't have enough room to put it on here and write at the same time. No matter what, when we're doing our double replacement or our metathesis reactions, we're always going to write that formula equation because that's going to tell us whether or not metathesis occurred. Does a reaction between barium chloride and sodium sulfate occur? Let's write these reactants down. Barium chloride is an ionic compound. So barium has a +2 charge, chlorine a -1. So BaCl2. Chlorine is soluble, so barium is not really on the list. Chlorine is soluble except for heavy metals. Barium is not a heavy metal, so this is aqueous. We're off to a good start. Sodium sulfate, another ionic compound, so sodium with sulfate. Sodium is a group 1 element, therefore it is always aqueous. You see sodium, it's aqueous. So we know there's a potential for a metathesis reaction occurring because all the ions are present in solution. This is going to be a double displacement reaction because we have two ionic compounds that are interacting versus a neutralization, which we would have an acid and a base. So a hydrogen containing compound and a hydroxide containing compound. So the barium is going to swap spots with our sodium. So we're going to have barium sulfate. So we have the 2 plus, 2 negative. So we have that balanced formula. Sulfate. So sulfate is in the water-soluble category. Its exceptions are group 2 metals, calcium, strontium, and barium. So barium is an exception to sulfate's solubility. Therefore, it is a solid. Then sodium is going to go with chlorine. And we see sodium, and it's going to stay aqueous. One product has to stay aqueous. Water's just not going to disappear, people. So you always have to have one aqueous product. So we're going to go through and make sure that this is balanced by putting a 2 there. This is a metathesis reaction. We can move forward. Now we're going to go into the ion equation. We're going to split out all the ions as they would appear in the solution. We have our barium ion, 2 chlorine ions, because they're in an ionic compound. There's a subscript 2, so there's 2 sets of them. 2 sodium ions, and a sulfate ion. On the other side, aqueous stays in their ion form. If it's a solid or a liquid, it stays as its compound. Barium sulfate is a solid, therefore it stays as barium sulfate. Whereas sodium remains as an ion, and chlorine remains as an ion. And that is our ion equation. What we want to do now is identify the ions that participated in the reaction and what we call spectator ions. So the ions that participated in this reaction are barium and sulfate because they are what made the solid product, which means any ion remaining is going to be what we call a spectator. They were there to make sure all the other ions were in solution when we started this reaction. So because chlorine is present as an ion on both sides, we cross that out. Sodium is present as an ion on both sides, so we cross that out. The reaction we care about is what we have highlighted, what caused the phase change. Our net ionic equation, the one that gave us the product we are looking for, is our barium ion reacted with our sulfate ion to form our solid barium sulfate. Notice that I kept the balancing all the way through. If there was a coefficient or a subscript, they went with their associated ions. So that can, our net ionic equation could have a coefficient with it depending on the elements we are working with. But this is the ultimate test of, that is the metathesis reaction. That is what we were looking for.